Shortly after I agreed to give this talk, I looked on the website and I saw I already was listed as talking about protocols. Now, that makes a lot of sense, but I figure all of you guys already know the protocols. There's no point in me giving a lecture on how TCP/IP works. So I thought I would give a history lesson. By the way, if there's anybody here who doesn't know how the protocols work, I can recommend an excellent textbook. All right, so let's start with how software gets distributed now. If you're a consumer, you hear about an app and you go to an app store, or up pops a QR code and you scan it, and you know that sort of stuff. And then when a consumer is faced with a really difficult thing, some message pops up that says you need to update your firmware, you know what they do. They call an expert. How many of you here are really low-cost IT support for your entire family? All right, that's the consumer world. What about the rest of us? Well, you know, you go to some repo and download things. There are lots of repos around. I assume everybody here has used at least one of these, right? How many? How many of you have used all of these? Unbelievable. I thought I'd put one on here that was a little bit obscure so I would find that somebody hadn't done it. Well, let's talk about the other side, how you distribute software. You upload it to a repo, to a file server, maybe at your institution. And the other side of it is you might give it to somebody on a flash drive. So that's now. Let's go back to before the internet. I got to Purdue as an assistant professor in 1976. Nobody had ever heard of networking. In fact, there was a faculty member, when I started working on the internet project, a faculty member took me aside and said, "Doug, you're throwing away your career." It was very, very serious. He was giving me fatherly advice. He said, "Older, you know, see, networking will never be part of computer science." This is a computer science professor. That's the way the world was back then. So, how about transferring software? Well, it really wasn't the same. The only way to get from one site to another was on some media. So you had to choose a medium. The two most popular for mainframe sites were punch cards and mag tapes. I didn't put down paper tape because that was really a niche little thing for people doing process control computers, you know, not the big mainframe stuff. So, punch cards. I brought one just for fun. I actually had to go looking for it in the back of a drawer somewhere. I used to use them as bookmarks. They came in colors. In fact, see how you can do block lettering? We did block lettering to plaster them on the front of a box. Cards came in a box, and if you went to a computing center, they had lots of empty boxes. You could pick one up, and that's how you transported around large programs. You got yourself a box, and to make sure nobody else picked up your box, you put your name on the front of it. By the way, I also brought this card because it is so fantastic. It's an old if statement in Fortran. And on the card, it's printed, the computer using this program may not provide this program to any other computer. It's sort of an early copyright thing, I think. But so when students picked up cards, this is what you got. You got this little legal statement on here. I don't know. It was a fun world back then. Anyway, you got yourself a box of cards, and it only held 2,000 cards. That means 2,000 lines of code. How do you fit big programs into small boxes? There was a common thing that we were told. You don't want your program to be more than 2,000 lines of code. We had to take courses on writing a compiler. We had to take courses, and those got pretty big. How do you make it not go over 2,000 lines? Real simple, folks. You take out comments. See, you think I'm kidding. All right, so a box of cards, a 2,000-line program that I wrote in grad school, I had to carry around a box. The boxes weighed 11 pounds. But cards weren't just for programmers. Lots of companies would put a punch card into a mailer and send it out, and on the punch card be written, put your address here, and you want our catalog or whatever it is, and send it back in the return envelope. And they would always give this line, which became a meme. Do not fold, spindle, or mutilate. There's I think it was a TV show, maybe it was a movie, where a kid asks his dad, can I borrow the car? And the dad says, as long as you don't fold, spindle, or mutilate it. It was part of the culture. So what were the other options? Well, the big option was mag tape. It was a sequential storage mechanism left over from ancient computers. By the way, did you know that early computers only had mag tape? A sequential medium for storage? They didn't have disks. So when you talk to anybody from the 1940s or 50s, that's the computing of the day. That's why if you took a theory course and learned about Turing machines, Turing machine is the mathematical abstraction of a computer that has a mag tape on it. It's not some fanciful, crazy mathematics. It's really practical. Anyway, I brought a mag tape to show you. Isn't that nice? It weighs 2.2 pounds. All right, so what can you fit on a mag tape? Well, a lot more than you can fit in a box of cards. By the way, the technology for mag tapes evolved. In fact, I was sort of near the tail end. I didn't realize it. When you're in school, you don't realize where you sit on the curve of things. But mag tapes had been around a long time, and they'd evolved, and they had higher density. What's that mean? Well, take the mag tape, and you wrote bytes sequentially on the tape. In the early days, it was 7-track tape because bytes were 6 bits. So they had 6 little heads and a parity bit writing along the tape. And in order to get more information on, they worked hard to make things more precise, and they could make the bits smaller so they get more bits per inch. The magic measure of tape, BPI, bits per inch. It's actually bytes per inch, but for some reason. But it went up a lot. It went all the way up to 6250 bytes per inch. In addition, tapes got bigger, same size reel, and you could get more on it. How can we do that? Well, enter the people that do material sciences. They figured out how to make tapes thinner, but the magic was without stretching. You're going to be pulling the tape through, and you have to make sure that it doesn't stretch. Anyway, how much data can you get here for 2.2 pounds? Well, look at this. 140 megabytes. You see this, 140 megabytes. If you really extended the block size to much bigger, you could get 170. But that was about it. Anyway, how do you read and write tapes? Well, you had to have one of these things. Big monster machines They did get smaller, especially in the late years of mag tape in the 1980s. As mag tape was fading out, technology got a lot better. By the way, only the upper part of these big boxes actually reads and writes tapes. So you put tape on a reel, you put an empty reel over here, you feed the tape through and wind it around, and then it would move the tape and write on it. But it was really hard to do that without stretching the tape, so it's hard to turn reels and get them right. So the reason these things are so big is down the sides there, all the way down to the bottom, are vacuum tubes. They are tubes literally filled with a vacuum. They suck the tape down. So the tape comes off of the supply reel, down through this tube that's sucking it down, up across the read-write head, down through the other tube, and up to the... That way, it's like a buffer. They could just keep turning the reel to fill this thing with tape down there, and then the read-write head would only have to move the tape from one side to the other. Okay, now we get to tar. It just occurred to me last semester that students in my class had been using tar all their lives, and they had absolutely no idea why it was named tar. And when I said, well, it was for a tape archive, they had absolutely no idea what a tape was. So before tar, we had programs to write files on tape, and what they did was they wrote the contents of the file. DD, for example. Popular way to write a file on a tape was DD. Have you ever used DD? Take DD to mention a file, mention a tape drive, /dev/RMT, whatever it is, and it would write the file. But Unix had changed the world completely. It changed programming in two ways. One, we had hierarchical directories. Now, Multics had to introduce them a little earlier, but nobody used Multics. Unix came along and did it the right way. It was actually very practical, and everybody was using hierarchical directories. Furthermore, the Unix guys preached the gospel of compiling separate files for each function. Put a little function in a .c file and compile it and get a .o file and another one, and then load them all together to get the program. So, lots of files, hierarchies. Tar said, here's what we're going to do. We're going to take an entire directory with all these files and a makefile and all the stuff in it and put it together and put it on tape. I used tar to put things on tape and to take them off tape for several years before we really had good internet access. And, and I'm not talking really early days when it was all still experimental. So we were building the internet. It wasn't building it out of stuff that we were doing ourselves. It wasn't reliable. It wasn't great. And finally, I realized what the real benefit of tar is. I can send the whole thing over the network. I can send a hierarchy over the network and reproduce it at the other end. So, did you ever wonder why there's a block size option in tar? I'll bet you never needed it. But if you were writing tapes, you had to write the right block size because you couldn't send a tape with a giant block on it to a machine, some poor user out there that had a tiny machine without that much space. I'm talking kilobytes. And you couldn't have a 64 kilobyte block on a tape because lots of people in those days only had 64 kilobytes of memory total. So you had to specify, you had to talk to people when they said, please send me a tape, they would say, oh, and make sure the block size is less than, give you a number, 8K. Oh, why do you want big blocks? Because tapes had an inner block gap. Between the blocks, there was a gap, and it was a fixed size that let the hardware figure out where the end was. So if you had bigger blocks, got more stuff on, but the other guy couldn't read it if he had a small machine. So you want the biggest block size that the other guy can read. Okay, how do we transfer across sites? Two options, hand carry or postal mail. And both ways, weight was really important. So I have computed for you the bytes per pound of the media that I talked about. Punch cards, 14,545 bytes per pound. Now that's actually a little bit wrong. It's characters per pound. And that assumes that I'm actually writing all 80 characters on a card. But if you were living back in those days, you were only supposed to write programs in 7 through 72. The N was reserved for sequence numbers, 73 through 80, and the beginning was reserved for a label. So really didn't get that many, but I'll give them the benefit of the doubt. How about mag tape? Bytes per pound. By the way, just for fun, I took my 256 gigabyte flash drive, weighed it, and computed the modern bytes per pound. So even if you were charged to send these things through the mail, it wouldn't do you much harm. Okay, so two ways to send things, punch cards or bag tapes. Nobody wanted to schlep boxes of cards. They're really heavy. Imagine 11 pounds per box, and I give you 4 or 5 boxes. It really gets heavy. Even mag tapes. Well, I was an assistant professor. I had to send things to people. I had written a compiler. I had written a grader program that was very popular. Would you believe it? When I got to Purdue, when I was in grad school and when I got to Purdue, professors, even in computer science, computed grades by hand. They literally wrote them down, and this was in the days before cheap electronic calculators. They did columns of numbers and added them and divided by the... I couldn't believe that, so I wrote a program to compute grades. And suddenly, people were using it all over. They would get these letters. Of course, it was all letters in those days. They sent me a letter saying, I understand you have this wonderful grader program. I'd like a copy. I would have to ask them what size blocks they could have on their, mag tape. And I would also have to ask them, can you pay the postage? In those days, professors didn't get any allowance. These days, it's the other way around. They get thrown money when they sign up to be a professor. You get a pot of money to spend on things like that. Anyway, there was some good news. If you had a really small program, you didn't have to send a big bag tape. It was a lovely little tiny mailer tape. And they were called mailer tapes. And the post office actually had little boxes that exactly fit these tapes. You slide them in. It was just so convenient. Okay. So what did the internet do? Well, we're going to go through a few things here. Architecture and systems, economics, blah, blah, blah. Internet architecture. Well, the phone companies owned networking in those days. In fact, AT&T used to talk about the network. Uppercase T, the, uppercase N, network. There was only one network, and as far as they were concerned, it was only one network in the world. It was the phone network. They said everything has to be in this one unified network. But the internet guys embraced heterogeneity. They said, we're going to use routers to interconnect arbitrary types of networks, which doesn't sound like a big deal now. But if you were on the other side, and everyone who had ever studied networks had always learned about the AT&T approach, everybody believed that was the only way to do it. The internet guys did a great thing because that meant you could choose a network for every situation. And you could incrementally upgrade your network hardware without affecting the rest of the internet. It sounds silly, but do you know how long it took AT&T to convert from dial telephones to touch-tone telephones? In order to make that work, they had to change everything. The whole network is all built into the network. So, what's it mean for you? Well, it means you can start with a low-cost internet connection and then upgrade. How about connected computers? The computer vendors in the 1970s and late 60s to 70s were building what they called computer networks. And every vendor had the following idea. We'll make more money if the network only connects computers from our company. I know it's hard to put yourself back in that position, but imagine that you're working on a network project, and I tell my colleagues, I tell other people, I'm working on this thing called the Internet Project, and they want to know, what is it? Well, it's a computer network. Oh, which company? None of the above. You can't do that. You have to know which kind of computer you're connecting in order to do it well. And certainly IBM and Digital Equipment, they had all come up with this line. You have to be able to tell all about the computer to build the right network for it. Okay? So what do we get? Well, from the internet approach, we get the opportunity to use whatever computer we want for whatever situation, and a big one, replace or upgrade that computer, maybe to a different model, a different vendor, without changing anything in the network. So, from the point of view of distributing software, that means a repository can start with a cheap small computer and upgrade and upgrade and upgrade. And maybe they decide that Intel isn't good anymore and they get ARM. No change to anything. Here's another thing that you probably take for granted. In the early days of the Internet Research Project, very few of us had little Endian computers. I was really lucky. When I got out of grad school, the guys at Bell Labs wanted to recruit me to work on VAX Unix. And I thought about it, and I decided to go to Purdue, which in those days was ranked number 7 in the world in computer science, very prestigious. And I thought, they also said, by the way, we're going to try and get better. So I thought that would be great. I like to teach, and so I went there, and the guys from Bell Labs said, tell you what, if you get yourself a VAX, we'll give you VAX Unix, and you can play with it and work on it. So I went to the dean. I was an assistant professor, and assistant professors never talk to deans. But I went to the dean, and I made my pitch, told him this would revolutionize the department. If we were one of the first departments to get this brand new computer and run this brand new operating system, Unix, it would be wonderful. And the dean surprised everybody in the department by coming up with the money to do that. Now, why is it a surprise? Because the cost of a VAX computer was almost exactly 20 times my annual salary. So, you know, we didn't have any money for facilities at all in the department. Well, we did have money. We had enough money to buy a new typewriter for the secretary in the department every 3 years. Typewriter, not computer, not. All right. So I had a VAX, and almost all the other guys had big Endian machines. John Pastel had a TOPS 20, which was the sort of high end of Digital's big Endian stuff. And he got to write the standards, So he said, well, look, IBM, the big digital machines, almost every computer in the world, and by the way, IBM controlled a huge percentage of the computers and software worldwide. At one point, I think they were actually coming down a little bit, but at one point, it was 95%. And they had big Indian machines. The IBM 360 stuff was all big Indian. So he picked big Indian and said, we're going to make all the internet standards big Indian. That meant on his computer, not a problem. On my computer, people would send me things and it wouldn't work on my computer and I couldn't figure out why. And it was because this Indianness stuff was not in the standard tool set that programmers understood. So not only do we have to come up with the idea of standardizing byte order, but we had to tell all the programmers, from now on, when you're writing things that may be used on another computer, and by the way, almost everything gets used on another computer, you better think about endianness. It was a real shock. Students in my class objected. It works on this computer. Why should I worry about what happens somewhere else? I think it was sort of a natural reaction, but so we get endianness from the Internet Project. Awareness of endianness and building programs that work across different Indian orders. How about internet services? Well, the phone company had been in business for a long time. Remember, they owned the network. And they said, the only way to build services is to build it in the network. You can't trust people to put services outside the network. Phone company owned the network. They put everything in the network. So what's the disadvantage of putting things in the network? Well, you know what call forwarding is. You know, where you have a phone and you can forward it to another phone. How long did it take the bright guys at Bell Labs and the bright workers at AT&T to roll out call forwarding as a new service? Years. Some people say more than 5, but at least 5. 5 years from start to finish to roll out something that seems pretty simple. That's because they had to go to every phone switch and rewrite the code in every phone because all the services were built into ESS number 4, ESS number 5. So the internet guys said, we're going to put the services outside the network. What do we get? We get wonderful results. In fact, it turned out better, I think, than anybody who was proposing this in the beginning actually realized. You can invent new services, like, for example, the World Wide Web. The internet was already up and running just fine, and we had all sorts of things on it, and then along came the World Wide Web, and we just, not a problem. It's not done in the internet. You don't have to change anything. You just add new computers running this new software, and presto. Oh, same thing for GitHub. It's true. And you can change services at any time. The internet approach to economics. Now, none of us on the Internet Project, at least in the core group, were economists. We were all techies. But we lobbied very strongly to go against what the phone companies had all done. The phone companies had always billed based on time and distance. Whenever you made a call, they would figure out how distant it was in miles, not in wires. You know, the wires might go funny ways, but they would figure out miles, and then they would time it, and they would charge you for that much use of the network. The internet guys argued and argued for a flat rate approach. So, what's the advantage? Well, here's the deal. Imagine that you want to go to google.com and you type it in your browser and it pipes up a little flash on the screen that says, estimated cost of this connection, 32 cents. Click here to approve. I couldn't imagine, we were doing TCP connections, not phone calls. They weren't phone calls that lasted for many minutes. They were just TCP connections. Can you imagine having to approve that? Or worse yet, not having to approve it and, well, you probably already know what it would be like. It would just be like you've gone to the cloud and the ISP sends you, the cloud provider sends you a thing at the end of the month saying, here's your network charge. You have no idea what you were using, how many bytes you sent across the network, right? Imagine that you did that with your home, and every end of the month, you would get this bill that says, you've used this many network connections, and here's the charge. But we had a reason to really push back against charging per TCP connection. What was it? One day, I visited Bell Labs a lot and talked a lot to Brian Kernighan of CFAME. And one time I was there and Brian said, well, I don't work for a phone company. Brian, did you resign from Bell Labs? No. They had done a study, and here was the study. Suppose we take AT&T, the whole shebang, including Bell Labs, right? All that money. Have you ever seen the size of Bell Labs? Huge organization. You know, at Bell Labs sites, one of the sites had millions of square feet of offices. Millions. Okay, so all of that, and they asked the question, how can we save money? And one of the things they explored was, suppose we didn't have to do accounting and billing for each phone call. We didn't have to keep track of that. We keep the phone stuff all the same, the maintenance, everything, but we don't do accounting and billing. Instead, we just take the total cost of running the network and divide it by the number of telephones in the country. The reason that they had started this was that phone bills had just pushed past, the average phone bill was pushed past $20 a month. Now you're saying that's nothing now, but go way back, $20 a month was a significant cost. What would it have been if they didn't do accounting and billing? Rip out all that stuff. And by the way, and include in that the postage to send monthly bills, or, you had to send the monthly bill and get back the answer and cash the checks. Over $20 a month on average, and it would have been less than 20 cents a month if they didn't do accounting and billing. So remember that when you think about why we pushed back on accounting for every TCP connection. Horrible. We would have been paying a fortune. So you can thank the internet guys for cheap, low-cost internet service. How about the communication paradigm? The other thing the phone companies had was asymmetric protocols. Everything was asymmetric. If you've ever worked on phone stuff, you know about the demarc, the boundary between them and us. They own things to the demarc, you own things on the other side of the demarc. If you haven't done anything with telecom, if you've played with RS-232 on a Raspberry Pi, maybe you've encountered the problem with the asymmetric protocol. RS-232 says there are two ends, a DCEN and a DTEN, and they send on different wires. This one sends on 2 and it comes out on 3. This one sends on 3. Oh, it's really ugly. If you ever had to deal with it, you'd understand. So, the internet guys said, we're not going to have asymmetry. They've actually fought hard because everybody's reaction in those days was to design an asymmetric protocol. They fought hard, and what do we get? Well, what we get out of no asymmetric protocols is that there are no application gateways, and there's no protocol translation in the middle. Now, forgive me, I'll excuse NAT because, that helped us a lot. You know why NAT helped us? Because the ISPs wanted to charge per computer at your house. And NAT just got around that. So they were forced, it all came out in the open, they were forced to back down. And what I really like is that later on, after all the wars and lawsuits over this stuff, once they had lost, they sent out a nice little ad saying, we've invented this new thing, we're going to give you a wireless router, and we're doing you a favor. Any case, what we get out of the internet communication paradigm is the ability to represent data in new ways. Doesn't matter. The network doesn't understand the data in the middle, doesn't change it. So we can do end-to-end encryption. You have to thank the internet guys for that. The phone companies wanted to have the encryption go between you and them. They would handle it, and then between them and the endpoint at the other end. So they wanted to have two forms of encryption. Here's a big one. You probably didn't realize that everything changed with the internet. Now go back before the internet, there were companies building protocols, and one of the standard ways that they built protocols was to use broadcast to find a server. In fact, IPv4, when it started, had network broadcast as a big feature. I could send a packet to MIT. I didn't know where Dave Clark's server was. I could just send a packet and broadcast it to MIT, and it would get to every computer there, and the right one would respond. That's all deprecated now, because after a while we realized that's a bad way to do business. Well, we didn't have to think very hard. Go back and read the history of Digital Equipment Corporation, LAT, L-A-T. LAT was used between terminals and servers, and it broadcast. And then when people started hooking up sites with satellite bridges, did you ever hear of Vitalink? They did satellite bridging back in the early days. As soon as they did that, broadcast swamped the satellite and swamped the other site. I'm going from my terminal to my computer here, and it gets broadcast to every site, and it was terrible. By the way, did you ever look at the early version of Apple Talk? Apple Talk loved broadcast. That's how they did hardware addresses. They didn't really build them into the computers. You would generate a random number, broadcast and say, anybody using 54 today? Oh, nobody, I'll use 54 as my MAC address. In any case, we had a wonderful guy, Paul Makapetris, one of my friends, who invented the domain name system. And we were all thinking about how to do name servers. Everybody was thinking. We knew what the problem was, and we knew we had to have it distributed. But Paul came along. He wrote up a solution, put it on the table, and it was so much better than everything else that it won. Hands down. one of those times when you realize there are really, really smart people here. You know, they're doing wonderful things. But his major achievement wasn't just that he had a distributed name server, that worked great, but he had delegation of authority. That was the major change. Everybody had been thinking like the phone companies. Let's have a group, whether we want to call it IANA, whether we want that owns names, and it will be giving out names, improving them. Paul said, what we're going to do is delegate authority. So you go to example.com, some company, and you give them the authority to do everything connected to example.com. You can have a computer named www.example.com. By the way, have you noticed that I am following the internet standards here? When you give a talk, you are supposed to use example.com. Did you know that? You can find it. It's written down. It's in RC. I just want to show you that I'm very, very knowledgeable about the protocols. But once you can do that, you can have a computer named mail.example.com. You can have subdomains of example.com. For example, if example.com is a big company and it's got subsidiaries, they can be assigned subdomains. Oh, by the way, Paul doesn't like it when anybody uses the term subdomains. But Paul isn't here. So this was a wonderful idea. It let us name computers for services. Now you don't have to figure out which computer at some site runs the web server. It's named www. Whatever their domain is. How about the invention of an end-to-end transport protocol? Now, when I first got into the internet project, I had to put IP over X25. X25 was a CCIT ISO standard. It was used by banks, and it followed what was then considered to be the absolute necessity. It did link by link positive acknowledgement with retransmission. So you have a bunch of switches along the line, and when you're ready to send a packet, you divide up the packet into smaller pieces, you send it to the next hop, and that would send an acknowledgement. Got that one, here's one, got that one, here's one, got that one, here's one, get the packet together, send it over the next hop. Here's a piece, got it, here's a piece, got it, here's a piece, got it, and send it over the next hop. It was absolutely horrible. So, the internet guys said, we're going to try and do end-to-end transport protocols. Reliability end-to-end. Everybody that I knew who had any kind of network background said, that's impossible. You'll never do it. You can thank Dave Clark, who spent at least a decade more of his life figuring out how to do end-to-end reliability without going link by link. It's so much better. Now that it works, everybody can see that it works well, and it's so much faster than doing all of this little back and forth across each link. Why did they think it was impossible? Because they said, look, we've built this stuff, we know how to do it, you have to know the round trip time on this piece of hardware before you can do acknowledgement and retransmission. You have to know it on this link, on this link, on this link. If you try and do it end to end, you have no idea what's in the middle. It's just this big mess. So Dave said, we're going to do adaptive retransmission, which completely solved the problem. It was one of those, another one of those brilliant solutions. And by the way, it does flow control, end-to-end flow control, so a big, powerful computer can send to a tiny little computer without overrunning it. It does congestion control in the middle of the network. One of the guys, when I first got on the project, he said, have you met Dave Clark? I said, yeah, I'm on this thing with him. Oh, he said, you should tell Dave Clark to give up. It'll never, ever work. He's wasting his time. I didn't tell Dave. But then about 10 years later, I met this guy again, and I said to him, well, you remember what you told me that I should tell Dave Clark to give up? Look, it's working. He said, oh, well, I guess I made a mistake. The problem was a whole lot easier than I thought it was. So, never back down. You can always find a way to not back down from a bad mistake. How about quality of service? Now, by the 1990s, quality of service was considered to be the most important thing we had to do in the internet. We couldn't survive without quality of service. Have you heard the apology from Scott Shankar? You've got to go listen. I think it's out on the web now. He gives an apology. He was one of the leading guys that said, no, we've got to have quality of service. We'll never do video or audio over the internet without quality of service. So when you make a connection, you specify what kind of data rate you need, what kind of latency bound you need, and the network will adapt and figure out how to do a path that will give you exactly that. Way back in the early days, the internet guys said, we're going to do best effort delivery. We're going to start with best effort delivery and see what it gets us. And everything seemed to be going along fine until we started to get a lot of traffic. And there was a really nasty surprise, something that no one really expected. You see, there was a huge amount of literature about how to engineer networks. It was all done by the voice guys. And it turned out that voice networks, when you take the aggregate of all the phone calls, come out very, very smooth. For whatever reason, you can think this is crazy, but it's not. If you have a phone call that's nice and steady, it's always sending the same data rate all the time, 64 kilobits per second. And when you add them all together, it comes out nice and smooth. With traffic, it's not smooth at all. Packet traffic is incredibly bursty, and when you take the aggregate, you get this giant bursts. So, we saw the problem on the ARPANET. ARPANET backbone had 56 kilobit per second links. It was slow even at the time. And as we started to add more and more sites, and they were all using the ARPANET backbone, yuck, things could get really, really bad. So, how do we solve the problem? First thing to understand is the relationship between utilization and delay. Maybe you've seen this. It's the only equation that I really like out of queuing theory. The effect of delay depends on the utilization in a packet switch network. Remember, this doesn't apply to phone networks. This is packet switch. So utilization goes from 0 to 1. What percentage of the line is being utilized? And you can see what the delay does. When utilization reaches 50%, the delay is double. But when it reaches 80%, the delay is 5 times as big. In fact, it looks like this. I stopped it here at 80% because between 80 and 100%, I'd have to extend this slide a lot more because the delay goes to infinity. So just go out a little bit more and see what I'm talking about. Okay, so how do we handle this situation? First of all, TCP has wonderful congestion control. You can thank Dave and Van Jacobson, who did wonderful congestion control for TCP so that when things start to look bad, TCP backs off. Your TCP in your laptop will do the back off. Remember, the phone guy said, you can't trust users outside the network, they won't behave well. And we've always had a few crazy people who said to themselves, I can rewrite TCP and get more of the bandwidth if I don't back off. When things go bad, I'll just keep sending stuff in and I'll get more. It doesn't actually work for them, but they've tried. Now we have agreed that it works well for all of us if all TCPs back off and do congestion control. In addition, we now have the 50-80 rule that says if utilization on a link reaches 50%, it's time to start planning the upgrade. When it reaches 80%, you're in terrible trouble. Because remember, it's bursty, so this is average. This little curve shows average, but the bursts can be really bad. Okay, so what did I tell you? I told you this. We get universal communication out of the internet. We get an architecture to allow us to use arbitrary computers and change them. Service model that puts the services outside the network. Flat rate economics. And then paradigm enables creation of new applications and the use of encryption and awareness of endianness so that we can write programs that talk across the internet and not even worry about that anymore. Client-server paradigm as you know it. No more broadcasting to 5 servers. And then transport with congestion control and technologies that achieve high performance. So here's my point. Everything you know and love came from all of this, not from just moving to electronic communication, but figuring out how to do it well and figuring out how to avoid everybody getting charged a fortune to do it. Okay, I'll stop there and take questions.
Hello? Oh, there we go. Well, thank you very much for the tour through internet history. I'm sure lots of folks I think in the room have probably touched on one or two of those things over our long careers, but not nearly all of them. So thanks. If we've got some time, we can do a couple of questions in the audience.
Raise your hands, I'll come to you.
And in the meantime, wanted to present you with a gift from the team as well for joining us here on your Sunday. But yeah. Where did Phil go? Okay.
On average, how long did it take to punch out those cards and also those the reel-to-reels, like the small and the big? Did it take hours? Did it take minutes, seconds?
Okay, so how long does it take to do punch cards? The key punches were actually very like typewriters, but they were harder to press. And they had to actually push a little thing through the card that made the hole. And the chad would fall out the back. So you could not type, even a touch typist could not type anywhere near as fast as they could on an electric typewriter. So it was much slower. That meant, by the way, the good news is that meant everybody thought hard about their program before they punched it. I'm serious. The trouble now is, I don't know about you guys, but I've seen students, maybe you have some new hires that do this, they sit down in front of the computer and start typing, hoping that the the computer will tell them, oh, this line is wrong, change it. While they're doing it. Don't think, just, try it out.
So no CI/CD in punch card land? You mentioned that it doesn't matter what Paul thinks about DNS because Paul's not here. About 3 years ago, Paul was standing in that exact spot telling us what he thinks about DNS and that we were all wrong. So there you go. Go ahead.
Yeah, so thank you for a great presentation. Can you give us the best lessons learned that you had in your career? And a funny one too, I'm sorry. Yeah, whatever.
Let's see, best lessons learned. Let me start this way. I was the first guy in my family to get a college degree. I didn't know anything about college. I didn't know anything about grad school. When I got accepted to grad school, I told my parents, and my father took me aside and said, "Does this mean you didn't get a degree? You have to do more school?" So for me, it's been a wonderful experience because when I finally got to the Internet Project, I felt at home. Now, you can say, okay, I'm just a nerd, but I was with PhDs, and I got to these guys. One of the things that's really inspiring is you need to prove a theorem, you can prove a theorem. I've written papers and proved theorems and published them. Other people on the Internet Project, when they needed to prove a theorem, proved a theorem. You need to build hardware. I've soldered wires together. We had a most incredible, but I had learned all that outside of class. I never took a double E class. I had learned that in my basement as a kid, figuring out how to solder things together. And that was sort of what I found at the Internet Project. These guys they weren't siloed. They were fairly broad. And they can go very, very deep when they need to. And so that's if you go to college, they'll tell you you can either be broad or you can be deep, but you can't be both. And it's really inspiring to meet people who don't have that urge to just do one narrow thing. And the other thing I'll say is I never really thought much about the authority of the experts. And that turned out to be really, really good. If I could do it, I did it. And I didn't listen to what them say, what you could or couldn't do. When I started working on IP over X25, a well-known expert in networking told me, that will never work. We're not going to do tunneling. We're going to do protocol translation, and we're going to beat the pants off of you. This guy had published papers in networking. I hadn't published anything yet. I was brand new. And it didn't intimidate me somehow. I just thought, I can figure it in my head. I can see how this will work. I can't understand why he keeps saying it doesn't. And that, I don't know, call it hubris, call it ego. I don't know what you want to call it, but I didn't think I was actually trying to put anybody down. That's the only way I could see to solve the problem, and it did work. So, there's a lot to be said for not listening to people.
Nick, thank you for coming out here, and to say the least, it was an amazing presentation. You become an associate professor at Purdue of everything. Why networking? Why was that the road you go down?
Pardon me?
Oh, I'm to your right. Over here.
What's the question?
Of all the paths to go down, why networking? Why was that the one you? All the different paths you could go down. There's
all
people.
the different paths you go down. So, I'll tell you something. When I was at a college that didn't have computer science, and while I was there, they got a digital computer. I was a math and physics major. I started playing with this thing. I asked the head of the math and science department, the whole division, I said, can I use the computer? And he gave me a key. He said, you can use it after hours. By the way, computers were rented in those days, not purchased. So I got to go in and I taught myself all bunches of programming languages, and I taught myself assembly language. I just loved it. It was just plain fun. And I was getting married. I told my wife, I'm going to go to grad school in computer science. And I had written some programs. I had written one that was really hard to write. It took me a long time. I figured it out. And later on, I was asked to clean out some file cabinets, and I found this contract. It was a consulting contract with IBM. It described this problem that I had solved. It was to a T. It was exact. They'd done a really nice job of documenting it. And then you flip it back and it says, we contacted 28 experts at IBM, listed their names. They all said it's impossible on that size computer. So I'm having fun. And I said to myself, that moment in I was standing there cleaning out this stuff, either I'm really, really good, or I looked at the price tag on this thing. It was 2/3 of my father's annual income. Either I'm really, really good, or in computing, you can get paid a lot of money for saying, sorry, I'm too dumb to do that. So I went to grad school, and it turned out that I was really, really good. So I just kept following the path of fun and, success.
I think we have time for one or two more.
As an industry, we're relearning specification and documentation. What are some ways you think about before you write the specification or the documentation, like some heuristics in your thinking?
So I have this funny thing about trying to visualize the whole shebang in my head. And here's a little thing that works for me, doesn't work for everybody. But when I get a hard problem, I think about it and think about it and think about it. I write down all the things that you have to solve this thing. I'm going to have an array of this, and I'm going to have this, and I'm going to have a module to do this. And I start to think about it in my head. And then I go to sleep. And several times in my career, I have awakened with the solution in my head. I told you about that program that I wrote that was, the IBM guys couldn't do. I had thought about it and thought about it and thought about it. I woke up and it was as plain as day. I knew exactly how I had to build the software, what the data structures would be, and I wrote as fast as I could. When this happens, I always have this fear that it's going to just evaporate. And in fact, it hasn't. So I just write it down as fast as what can I say? That's something I think hard about, the whole big problem and all of the sort of trade-offs. If you do this, it's going to cost more here, but it's going to relieve this. What kinds of parameters do I want to have for each module? What kind of, how do these things talk to each other over a network? And I think about it until I get it sort of a picture in my head. And then I start to write the basic specifications.
Yeah, we can do one more. Just many years ago, networking was the thing that most, that got you most excited, what you spent your career on. Thinking about today and sort of what the types of things that this audience is working with, what gets you most excited, and where would you like to see us focusing as the next generation here?
So I have this feeling that I got into computing at the right time. I got into computing, I didn't realize it, but it was still a baby. I got into computer science at the right time. I didn't realize it. I just thought the professors were, I don't know, blind. You could do these courses so much better. You could do this kind of stuff. You could do that. And so I was very successful in making all those changes because it was very early days. One of the things that sort of hits me now when I look around at computing, it's no longer early days. Even cloud is no longer early days. AI, machine learning, you know how old it is? Machine learning has been around since BC, before Comer. It's really old. And just to make a list of every possible variant of machine learning, let alone all the other applications and uses. And so I don't get excited by that. Here's a mountain to climb. I get excited when there's not much in front of you and you have to sort of create from scratch.
Do we have any more questions? Oh, right in front of me.
Thanks for a great talk, Dr. Comer. I enjoyed the trip down memory lane, some of it before my memory. I wonder, it's always easy to talk about, like, hindsight's 20/20, but I wonder if you can talk a little bit about, like, the road not taken. For example, I think about, like, multicast. Like, I remember in the 90s, like, hey, if we could just turn multicast on all the tier 1 routers, then, like, we wouldn't need YouTube. We could all distribute media to everyone, to infinite people, as many as we want, and it just never happened because the people that had to turn it on the core routers were the exact same companies that were going to end up selling stuff. I wonder, in that kind of sense, if you think about, like, not necessarily mistakes that were made, but the road not taken that maybe you wish we'd taken, or maybe we got there the long way.
Okay, so I could give a whole lecture on multicast and why Steve Deering was wrong to start with and why we should never have gone down that path. And it wasn't just the economics of, it was that multicast doesn't scale well. But anyway, what about things not done? I don't know. I don't have any big things that I wish we had really done. I do believe the following. The guys that I worked with on the Internet project are the smartest people I've ever worked with. I work with PhDs, right? I'm in the university. I'm around PhDs. These guys stand out among PhDs. Then they don't all have PhDs, but they stand out. They are really smart. I believe that if they had decided to do a connection-oriented network, we would have one fantastic connection-oriented network because they were relentless, they were smart, they worked hard to figure out how to do things well. So I'm not sure that there's any big change that we could have made that we didn't make.
Yep. So I think we'll call it there. Thank you, Dr. Comer, for joining us and sharing with us. Thank you to all of you for joining us at Scale. Hope to see you here again next year.